right, everybody, let's wrap up our discussion of regression in the context of hypothesis testing. So we're going to take that same scenario that we worked with last time. We have this general question of, does high school GPA predict first-year college GPA? So we have to take our that question and make it more specific, more technical for our research question. So really with this, and the way that this question was phrased, all we had to add was significant. So does high school GPA significantly predict first-year college GPA? Adding that technical term is what makes this more precise, because we're dealing with statistical significance in hypothesis testing. So here are some things the question needs to include. You have to have two continuous variables that are being examined. And you know that you are dealing with predictive relationships. So it's not asking, are they related? It's asking, does one predict the other one more specifically? Now, we have these same 7 steps, okay? The hypotheses, calculation, and the crit is going to be slightly different, but the same comparison, 5, 6, and 7 is the same for linear regression as it is for all other inferential stats. So let's start with step 1 with the variables. So the first variable that's mentioned is our predictor variable. So that's going to be high school GPA. It's continuous, and high school GPA ranges from 0 to 4. And what is it predicting? It's predicting first-year college GPA. So that's our dependent variable. That is continuous variable, again, ranging from 0 to 4. So we got our 2 variables here, predictor and our dependent variable. Now, how do we do our hypotheses? Well, the benefit about regression hypotheses is that they are always non-directional. So the question will be non-directional, the hypotheses will be non-directional. So the question asks, does high school GPA significantly predict first-year college GPA? The alternative says it does significantly predict. The null says does not significantly predict. Essentially, the alternative is saying that the slope, will not equal 0. Because if it doesn't equal 0, it means there's some type of predictive relationship there. The null says that it will equal 0, because when b equals 0, there is no predictive relationship between your variables. So let's use the example that we used last time. We have these 10 high school students, and we gather their high school GPAs at the end of high school, and we gather their college GPAs after their first year in college. And we have a research question on hypotheses, or in our variables. And then we have our slope. Slope is what you use to do hypothesis testing in a linear regression. Now, the slope that we get, we can't use the slope directly. What we have to do is we have to convert the slope to a t-score in order to test it for statistical significance. So the way that we do that is we take, well, again, the slope is the covariance on top, standardization based on only x's on the bottom, okay? The slope is the degree the predictive variable predicts the dependent variable. And in order to convert it to t, we have to first get something called the standard error of the slope. Standard error, so it's a measure of sampling error. And we use that and plug it into the t equation with the slope on top, standard error of the slope on bottom, and that's how we get a t-score. So let's go ahead and calculate those things. Okay, got our slope right there, 0.695. And then we need to plug in for our standard error of the slope and our t-score. If you want, pause the video, try to calculate those numbers, and then continue on. So the standard error of the slope that we get is 0.302 by plugging in all those different things that we have here. We have the standard deviation of x times y. We have the standard deviation of x, square root of n minus 1, which is 10 minus 1, so 9, right? And we get a 0.302. So that's our standard error. So remember, that's the closer to 0, the less sampling error we have. So 0.302 is not too bad. We plug those two things in t equation, and we get a t-score of 2.301. Okay, so now we can go back and continue on. So when we have our t-score, we have to compare it to a t-crit, so we can determine how likely we were to find this relationship, represented now by this t-score. So to find the t-score, we need to go back to the t-critical scores table, okay? And the way we do that is it's always going to be two-tailed. So we're always looking at the two-tailed side because regression is always non-directional. Alpha is 0.05 and degrees of freedom is n minus 2. So take the sample size minus 2 and you get your DF. So go ahead and find that on the t-critical table. Two-tailed, alpha 0.05, n equals 10, and then continue on. So the t-crit you should have gotten is 2.228, and that's going to be plotted on both tails, so it's positive and negative. Now, does our t-score go past either of these crits? okay? As we can see, yes, it does. 2.301 goes past 2.228. So because it goes past, we know that it has a probability less than 0.05, which means that it was unlikely, assuming there's no predictive relationship, assuming the high school GPA does not predict first-year college GPA, it was unlikely for us to find this prediction that we found. So that's evidence against the null, so we're going to reject it. We'll take the alternative as our conclusion. We restate that as the conclusion. And all you need to do is just put this back into the general language for the general conclusion. High school GPA predicts first-year college GPA. And then lastly, we want to represent this with a scatter plot using a regression line to show, just like we saw in our last video, to show the predicted values of Y with the actual values of Y. And that shows us the predictive relationship visually here. And so with that, that is how linear regression works in the context of hypothesis testing.